I'm supposed to moderate a discussion here, and I think this means asking questions of students here. I'm used to doing that. So let me start with Jocelyn. You know, I have a confession. I hate sensors. You know, I tell my students they're the creation of the devil from a software standpoint because they misfire so much in my experience. And you mentioned this word robust. Mm-hmm. I'm wondering, do you think we can get to the point that they're robust enough that we're not being plagued by false positives from your wonderful technology?
And I think that's a really important and a really good question because especially for some of the applications that we're looking at, false positives could be a problem if you have a sample that's made up of lots of different things. You're looking for one thing, you get another thing reading out instead. So I think you'd have to design not only the device that I was talking about, the mechanical part, very nicely, but you'd also have to design the part that, the computer part, the part that reads out that sensor and really integrate that as well to sort of help eliminate that problem. I think it's a bigger design problem to really get that sensor so that it doesn't misfire and it doesn't give you that false positive. Is it possible to be 100% accurate 100% of the time? I'm not sure.
I'm sure there's no sensor on the planet that's achieved that, right? So let me ask a different flavor. What I'm used to is you don't use one sensor, but you use a whole bunch, and then you kind of, I mean, the simplest motion is you take a vote among the sensors. Yes. And say, and exclude the outliers and so on. Is that that's sort of more my area of software that looks at these sensors as a creation of the devil and tries to figure out who's telling the truth and who's lying. Is that applicable in your technology, do you think?
Definitely. So these devices are very small. We can pack millions of them onto a very small area. So you could have many devices running in parallel. We can actually miniaturize a lot of different components as well and integrate a lot of it on the chip, just on the small area. So you could have devices running in parallel to sort of give that voting system, I guess, and try and eliminate those false positives. For sure, that's an option.
Okay, okay. So near amazing technology, I usually am explaining to people how long a nanosecond is, but computers haven't gotten down to that scale that you're dealing with. But I guess it seems like you're working on some technology that has great promise. So, you know, this classic Silicon Valley thing, like let's take this out and start delivering that to people. What's the roadblock here? Why shouldn't I write you the big check right now?
Well, first of all, you should.
Oh, okay. Good answer.
Well, okay, so it's a great question. I can answer it in different ways, but from first aspect, there is the technology itself of the femtosecond, which is, it's fairly fresh, and these devices, like each femtosecond, box is about $100,000. So for practicality, for many applications, there's this limitation. The other thing is, a lot of the things I presented today, it's really in its infancy. So, just the attachment, we just came up with this in this February. So there's still so much more to learn about this before we take it. However, beside a few more years of studying and perfecting it, I don't see why it wouldn't go out. And you write me a check eventually. But there's so much to learn. I mean, a lot of things that I show here, I skip many, many steps and many things that kind of look obvious here, but they're so not obvious. Just, for example, just moving around neurons in a dish like this, like I was moving them around, just this took us about 6 months to achieve. So there's still a few more years to go, and probably then.
Okay. And is there anything you could see that, society would really benefit from this technology right now. So how do we make this go faster? Get you to sleep less?
Actually, in the short run, my goal, so I mentioned further research. In the short run, really what I wanted to do is we're building a tool that at this point can help researchers to study more in cell biology, neurobiology. So, you know, attaching cells, attaching neurons to each other, it's something that haven't been done before in any means, not just with this technology. And so what we're trying to figure out is, okay, we attached it, but now what? And people haven't studied this and said, let's cut it, let's attach it, and let's see what happens. So I see this immediately as a tool that can be used by doctors and researchers to just study the effects of this and just discover the potential.
Oh, so you view you're delivering or producing an enabling technology for people in medicine to figure out how to apply it. Is that? In
the short run, I think so. Yeah. In the long run, I think it can be actually being developed as a bigger tool. But in the short run, I think this is what it is.
Okay. Thanks very much. I think everybody was expecting me to ask the same question to everybody, and I'm not good at that. So, Catherine, a classic question that gets asked in Silicon Valley is, so what's the competition here? And,
that's a good question.
We're just about to go out and solve this problem for amputees and so on with prosthetics, and I think it's a great problem to solve, but there must be other ways of doing this, isn't there?
There are. There's a multitude of different ways that this can be done. So kind of, I guess the advantage of the way that we're looking at it is we want to develop a system that the amputee can put on in the morning, they can go to work, use it, and then they can take it off at the end of the day, and they don't have to worry about things sticking out of their arm or anything like that. So it's a very non-invasive way that we're focusing on. But there's all kinds of different research out there right now. So there's groups that are looking at tapping right into the nerves themselves and sending signals up that way. They actually, I think this is in Chicago, they just released this within the last month or two, but they've put these little tiny nerve cuffs directly around those nerves, and they can electrocute the nerves and send the signal up to the brain. And they're getting all kinds of feedback out of this, not just pressure, they're also getting temperature, and they're getting vibration. So I think that's a really promising area, but it's kind of a bit further into the future. So right now, they've still got wires coming out of their arms perpetually. And so there's still a few things that they need to figure out, check over the long run, over 20 years, is this still going to be feasible? Are they going to, is the body going to reject it eventually? We're not sure yet. So our solution is kind of something that we can work on right now, and we can get it out there really, really quickly. So that's kind of why we're focusing on this sort of simplified mechano-tactile design.
So I always tell people that this is more of a computing thing, but us academics go after an elegant solution, and occasionally you get ambushed by somebody who does the hack, sort of something that gives you 90% of the benefit, 10% of the cost, and this is so deadly it sort of makes me shake a little bit even as I talk about it. But so here's a hack for you. Supposing I say, well, Catherine, what I'm going to do is I'm just going to put sensors in the arm, and it's going to transmit Bluetooth to a smart watch that I'll get them to wear on this prosthetic. And so they just look at the hand, and it says, don't squeeze the egg anymore.
Yeah, so I'm not sure if that exact solution has been looked into. So I guess I can go a bit broader too. So there's not just, like, what we're looking at is intuitive feedback. It makes sense, you feel it, you don't have to interpret anything. But there's a multitude of other ways that you can provide this sensation where you have to sort of interpret something. So for example, if you're using your thumb, a cello will play a note. And if you're using this finger, a violin will play a certain tune. And it'll change for which finger you're using. So, but then you have to sort of interpret. You have to learn the tune of that note that's being played, and you have to know which finger that means, and you have to interpret it. So there's a big cognitive load associated with that. So you have to really be conscious of listening and doing, knowing what your hand is doing. And that's not something that you would do naturally. So a lot of amputees, they've tried systems that maybe vibrate when a certain joint is working. But you have to really be thinking about what that means at all times. Whereas, with another hand, you can just go pick something up. You don't even have to look at it usually. So typically, then they'll start using their other hand that's not a prosthetic arm, and then they'll run into overuse problems, or they'll have issues with two-handed tasks like folding a towel. So there is substitution methods. I don't know about Bluetooth and smartphones, but
Smartwatches.
Smartwatches. But yeah, there's definitely areas that are looking into that as well.
So you think that it's the sort of learning and non-intuitive element that's going to save you from being overwhelmed by some hack like that?
I think so. Yeah.
Okay.
Yeah.
Okay. Sounds good. So back to Jocelyn here.
Yeah.
So I noticed you put versatile on your slide, and one of the things I find is a interesting, different view between academia and the real world, especially entrepreneurship, is that a key requirement I find in forming a company, commercializing something, is focus. And focus is the opposite often of versatility. And so if I was trying to write you a big check, I said, well, Jocelyn, just forget versatility. Let's pick one area and nail it.
Right.
What's that area you would pick?
How fast do you want the technology?
Money's burning a hole in my pocket. Okay. I want the return as fast as possible.
As fast as possible, okay.
And it has to be married with another thing that academics don't like, which is, it can't be something that applies to only balalaika players or something. It has to be a sizable market where there's a total addressable market that makes sense to commercialize.
Right. So I think in terms of market, probably the best applications to focus on would be that biosensing type of angle. But I think that's also one of the more challenging ones to develop, because that requires, if you want to do a good sensor, you want to put that right in the biological environment. You want to take a blood sample, a urine sample, put the sensor in that, and then we have to operate in liquid. And that's the challenge.
Then you have to operate what?
In liquid, directly in, if you want to do this
right.
testing directly in situ, in a sample, a blood sample, a urine sample. So that's the biggest market, but also the biggest challenge. To do things quick and easy and still have a big market, I think the defense sensors are probably the way to go. But I have a funny feeling that the US military is probably way ahead of me, or other research organizations. So I guess in that sense, you're looking at a saturated market, perhaps. So I think in terms of focus and achieving that market, if we can break that barrier and get these working well in liquid, then it's a good product, and you can focus in on a specific sort of biological sensor application.
I actually would pick the defense sort of sensing market, because I shouldn't say this, but I moved to the States and I got dragged into reviews of defense things in Washington. I was expected somebody to say, is everybody an American citizen? And nobody did, and I sort of sat there with my head down. But back in the good old days of Ronald Reagan, I remember thinking, I hope the Soviets are more screwed up than our people are. And I couldn't believe it when I said it. It turned out to be true, but I think I think there's a need for technology there, and sort of saying something positive about that crew is they're very aggressive about taking on new technology, because there's a significant risk that they're dealing with, and so there's probably an opportunity in that area. And I don't know exactly, I haven't followed this in Canada, but in the US, one of the biggest barriers to medical innovation seems to be the federal government, the FDA, that seem to dislike anything that their grandfather didn't do, and probably being unkind, but there's a huge barrier to getting anything deployed because of government regulations. So defense and that sort of sensing that you had there, I think, would be a pretty attractive one. So let's see. I'm probably saying more than I should be saying here. Near, I guess, I'm not sure I've got a good entrepreneurial question here, but let me just ask, I'm probably too obsessed with reliability and robustness, and do you have a sense of, is this technology something where you think you can make it highly predictable? Like you mentioned 6 months to do something. Does that mean that now it'll take you a day, or is it likely to be 6 months to do it again?
When I mentioned the 6 months, it was to figure out how to do something. So now once we figured it out, it's a lot faster. But with this technology, making things happen fast, it's definitely possible, because here, all we rely on to make it faster is just automation. And so we use this technology to different medical applications in our lab. But one of the biggest things, for example, that we're working on now is automatically targeting certain locations and then releasing the laser pulse. But once we figure out all the parameters that we need to perform the attachment or destroying a cell or cutting a cell, from there on it's mirrors, it's motors, computer, moving it where you need to, and here you go. And so, for example, eye surgery, LASIK, that's done. So it uses a similar technology, but to scan this much of a space in your eye, if I would have done it manually, it would have taken me maybe a week. But because of automation and tracking, track the eye, the movement, and then it targets it and moves it into the right place, and it takes you 5 minutes. So I think it's definitely possible. It just needs to more development.
Thanks. So Catherine, and I don't know whether you've experienced this yet, but I must admit, just speaking from my own standpoint, one of the things that motivates me to be involved in industry is that it's this frustrating element to innovation university where you work real hard to develop something, you build this thing in the lab, you test it out, you write up a paper, you publish it, and then it stops. The grant runs out and so on. You think it's so great if you really believe in this stuff to be able to do technology transfer, and I could get into a whole spiel where many people believe there's companies sitting out there just waiting for new ideas, but everybody's busy in their own agenda and things. So often it means you going out and doing this. So have you thought about this? Can you see getting to the point where you say, if the world really needs this, I'm going to be the one that carries it forward, delivers it to reality?
Yeah, so so the one really, really awesome thing about my lab is that my co-supervisor, Dr. Jacqueline Hebert, works at the Glenrose, and she's actually the lead of the amputee program there. So we actually do get to work directly with amputees. Like, they come in and volunteer their time, and they try out our systems, and they give us feedback, this is not working, this is working. And so we do kind of get to take it that step further and actually, get it out there to people it's actually going to impact, which I think is something that's really, really rewarding, getting to work.
But it's still experimental,
It is still experimental, yeah. So we haven't settled on where we're moving forward. I think we need to validate it first, make sure it is working, making sure it's going to actually provide that extra usefulness to these amputees.
Yeah, I'm giving you the optimistic view, so you've
yeah,
gotten beyond that.
Exactly.
And
there's no reason we couldn't move forward and get this, commercially designed. I think there'd be a lot of challenges this would face. Right now, our design is, we're using stock parts off the internet because that's easier to integrate. We're using 3D printing, and that works for small scale. But if you want to go larger scale and mass manufacture this stuff, you have to look at different manufacturing techniques, different electronics. So it's a whole new kettle of fish. But hopefully someday we'll get there.
I usually describe it as a pain in the butt, but I guess kettle of fish will deal. But you have to have that passion to want to do that.
Absolutely, yeah.
Are you going to save the world? Are you going to do this?
I'll try.
Not to put you on the spot or anything.
I will try my best.
Okay. How are we doing for time here? Do we have? We're done. Okay. Yes, Matt.
Maybe we can open it up for some questions from the audience as well at this stage. Yes, right there.
Sure, yeah. I mean, there's always things that you can improve. You're always going to be getting feedback and creating iterative processes. So right now, it's getting smaller, but we want this device to be completely compact. If you could have it as just a little bump on their prosthetic socket, that would be, optimal. That would be perfect. So definitely working on getting it smaller and smaller would be something that would be really, really interesting to look into. Yeah, we haven't really thought as far forward as marketing and that sort of thing just yet. But I think in the long run, there's definitely a lot of improvements that we can work on.
So Catherine, can you talk to Jocelyn and have Nanosensor to make it really small?
Yes, I think so. We should.
Yeah, maybe we can move near over to this chair.
Well, if it's really fast, that would be helpful too.
But ultimately, that's what you're trying to do, is shrink it down,
Yeah.
use sensors, and if you had a multiplicity of small sensors that we're all focusing on it to eliminate the error rate.
Yeah, absolutely.
And then you get a better vacuum seal because it's not quite so moving.
Yeah, definitely.
Sounds like we're there.
I would like to ask a question.
Question?
And this is to Nir. Now, I'm a bit biased when I'm going to ask this question of Nir. Nir, I see a surgical tricorder pulling nerve cells together for someone who has a spinal cord injury of what you're doing. Tell me, from that end that I'm talking about, and I'm not talking about just nerve cells, we're talking about muscle, we're talking about different things that you could do. How long would it take you from what you're doing today to getting to that end product? And that is a commercial product.
That's a very good question. But to be honest, the way I look at it is there's an accelerator in this process. And I think the biggest accelerator is money. Obviously, if I had $2 million, then I could make it in a year or two, maybe, right? But as a grad student, it probably is going to take me a little bit more than this. But in actuality and in practicality, I think if we seriously have all the resources we need and we keep developing it in a fairly fast pace, then we can do it in probably 4 or 5 years, I would say. Something like this.
What would that mean to medicine? What would that mean to humanity?
There's something I keep referring to, and it's something a little bit more imaginative. So imagine someone need to do a brain surgery, and today it's considered inoperable because, if we're going to go into this place, we're going to cut neurons, we're going to damage more than we're going to do, more than we're going to benefit, so we're not going to do this. And so I think that with this technology, potentially, we can completely change the face of medicine because imagine you have a tool that can repair all this. So you have a surgeon and he'll tell you, yeah, it's okay, we'll just go make a surgery. If we cut anything, we'll just fix it after. It's not a big deal. So this is like looking a little bit into the future, but I think this can potentially change the way we think about medicine today, right? About surgery, about tactics of doing things. So I hope it's going to happen one day, but
Question over there?
This is Vernier. You may recall can you hear me? That there was a technology using pulsed lasers for attempting to do nuclear fusion power with little pellets. And I don't think it used femtoseconds. It wasn't that fast. I don't know whether femtoseconds is too fast for a technology like that, because you were talking about this signal going so fast that it didn't even affect the atoms that are there, so maybe it couldn't fuse atoms. Or would it potentially, a more powerful version of this, be useful for a pelletized fusion power source?
Okay, I know there's someone in the audience here who is actually dealing with this in this field, so he'll be better answering this question. But I'll be honest, it's not my field, so I'm going to try to answer, but it might not be a very good answer. But in my presentation, I tried to simplify many things in regards to the technology. So this, I don't know, and the person will correct me if I'm wrong, but I think they're using femtosecond. Yes, they are using femtosecond for this. He's right here in the middle, by the way. So, yeah, he can answer. It's easier. Sorry.
Well, I can probably talk to you after if you're really interested, but I'll be very quick, not to take the focus away. But there's multiple approaches to nuclear fusion. Femtosecond lasers are one of them. It's called direct drive, and there's techniques involved with that where you use the very fast femtosecond pulse to ignite the fusion reaction. There's other processes that are well developed that deal with nanosecond pulses instead, and very, very high energies. We're looking at megajoule level laser pulses, which is extremely high. Those are another process where you don't use that extremely fast pulse. So there's a lot of different ways that they're looking at doing it. But we can talk after if you're interested.
Another question? Maybe right here in the middle?
I'll repeat. I wanted to ask a question about some nanosensors and your ability to change the coating, therefore maybe what atoms or molecules you would attract. Is it possible that you'd be moving in a direction of replacing some of the big instruments you talked about, gas chromatographs, for example, in an application in which you know the components that you're trying to measure?
So if I understand correctly, you mean if you have a known
Yes.
sample and then use our technology to measure?
Correct.
Yeah, actually, we're working on that in our lab right now, believe it or not.
Okay.
So we do have the ability to in a gas chromatography-like system, separate out the different components and just feed them in to our sensors one at a time. And we can actually already do this, yeah.
So if you had a flue that would be feeding this lab on a chip type of thing, and you did multiple measurements to eliminate the false positives, what else is required on the electronics side to interpret the sensor's information?
And the electronics side, I think, is a big challenge, because right now in our lab, we use a lot of electronics to kind of compile and collect that data. I think the best way to do it, maybe if you can have some computerized readouts, so you have your little lab on a chip thing that's attached to a USB key, and you could plug it into the computer after for analysis. That might be one way to do it. Some of it could be miniaturized, so you could make it smaller, have sort of a built-in processor as well. I think the electronics is a challenge still to try and get that all scaled down. But we need something basically that can help us track that frequency. And just to put it in perspective a little bit though, the gas chromatography system that we're kind of playing with in our lab right now is about this by this, whereas our frequency analysis tool is about this big by this tall and that wide. So if we can just use that, we're already shrinking things down. It doesn't really help with the cost end of things, but if we can have something that's a little more specialized, then that could help out as well. So,
Thank you.
There's a question right behind, just past behind you.
Hi there. Question for Jocelyn. More technical. Once the molecule is attracted to the substrate, is there some way of getting rid of the molecule to keep that substrate free for another analysis, or is this a throwaway?
Well, there's kind of two ways to look at it. So the first way is just to kind of do a throwaway. So these chips are pretty cheap to fabricate because we're using standard computer processor manufacturing technology. So you could do just a one-off, single use. If you wanted to reuse the chips, it would be possible for certain types of molecules to stick on. You can actually heat them up, and the molecules will come off as the heat energy pulls them up off the substrate. So that's one way to do it. There's also chemical cleaning techniques that you could use as well if you really wanted to make sure you could reuse the sample.
Is it probably cheaper just to throw the chips away?
Sorry?
Is it less expensive to throw the chips away and just have a fresh batch? Or it depends on what you're sensing?
It depends on exactly what you're looking at and how much is integrated on that single chip. So I think it may be cheaper to have it be a one-use kind of thing if you made just a small removable part that plugged in and out of the rest of the electronics or something like that, for sure.
And if I might hog the microphone for one more moment, question for Catherine. With the sensors, you're pushing down on the skin. A couple of thoughts that popped to my mind. Has anybody looked at thermal gradients on the skin? Is the skin sensitive enough to determine or to detect the changes in temperature instead of a mechanical force?
Yeah, so as far as I know at least one group that's looking at that. I don't think they're doing point temperature. They're kind of doing an overall sort of radiating temperature. There's a bit of a debate, I guess, in the community about whether you want to provide everything that's happening or just a couple little things so that they can kind of, get the useful information and not be overwhelmed by what they're being provided with. But there are a few groups that are looking into temperature, for sure. Yeah.
Thanks.
Right, another question as we get to one way back there. As we get to that question way back there, Jocelyn, when you're thinking about profit, it's always better to create a disposable that's thrown away so it has to get replaced frequently. And remember that Ford at one time developed cars that rusted faster, so we would replace them until everybody caught on. So the ultimate disposable. The other side on that is there were two sides to Dr. Cheriton's point. You can either sell a very small number at a really high value, that's the military application, or you can create an entirely different market, which is who knew that all of us wanted to walk around texting everybody else in the world simultaneously forever? That market didn't exist. So what is the entirely new market? I'd give you the hint that in the environmental sensitivity that everybody is developing these days, that the personal hypochondriac market. And so the desire to test your water continuously every day, and you just buy a big pack and you test the water every day, that you would actually probably find this huge and growing market. And you have to use the marketing firms to convince people that they need to test it every day to feel safe, even if they don't need it. Why else are we drinking water out of plastic bottles when the water of the tap in North America is perfectly safe? So always think of markets that don't exist, which are large and disposable. So that's my 2 cents worth. I'll invest in that one. Question back there.
All right. So this is more of a general question for all of you. I'm a first-year engineering student here at the U of A. And just a general comment, I noticed that there aren't a lot of young people around here, although I was hoping that there would be because it's happening at the U of A. That said, I'm really interested in getting involved with research, and I noticed in Catherine's little spiel here, it says that you work with programs such as Discovery and WISES, as well as a lot of mentorship programs that sort of seek to develop this capacity in younger students. So for people who don't have expertise in particular fields, such as what you guys are doing, how do you suggest us getting started without actually having the technical expertise after having graduated from a program as such?
The easiest way is just to talk to your profs. Find out what your profs are doing and see what you're interested in. This is kind of a specific tip, but there's a Dean's Research Award program. And it's basically you get paid to do part-time research during your school year. So a lot of profs are happy to get a student to come in and see their lab and try out new things. And so you can kind of get an idea of what it's like to work with that supervisor as well as work with other grad students in labs. So I would recommend probably checking that out first. But yeah, attending lectures like this and kind of getting to see sort of what's available and what's out there is definitely useful too. Because you kind of go through undergrad, you maybe don't know what all your profs are researching. But go talk to them after class and see if it's something that you would be keen on helping out with.
Awesome. Thank you very much.
And if you're interested on that, that's run through the Faculty of Engineering, the Dean's Research Award Program. And if you were to speak to either me or Associate Dean Stephen Dew, we could help make the connection. We have several hundreds of these every year now of undergraduate students at all levels working in the labs with the professors, getting that first experience, and many of them eventually publishing papers, and then, of course, we want to see some of them creating new ventures. We don't see too many of them yet, but that's the other thing. Ladies and gentlemen, I know we could go on for quite a while with a large number of additional questions, but the clocks are all 1 hour fast. We're precisely at 9:30. We had promised everybody that we would bring it together about here. I know we could handle a lot more questions, but I think there might be some opportunities for one-on-one questions right after. But please, ladies and gentlemen, join me in thanking our three great students, Jocelyn, Catherine, and Nir, and Dr. David Cheriton for moderating and stimulating the discussion. So thank you so much today.